So later on, you can see in this I've given some more of the things like defining a deep model and then analyzing model summary. You can go through this. These are pretty straightforward things. There's not much in that. Okay, you can go through them on your own time later on. If you have any doubt, you can easily ask any of the TAs, and all the TAs had been in that mail. That was so you can ask any of the TAs related to the doubts later on. Okay. Now what I'm going to do is I'm going to move to TensorFlow 2.0. See, the problem with Keras is you can see how easy it was to make a network. So there was just 5 lines to make a network, 1 line to compile and 1 line to train the network. So 7 lines and my network is complete. Right. So Keras, yes, it's very easy to use Keras when you're using deep learning models, but Keras, you can only make deep learning models. Okay. Keras does not allow you to make custom learnable functions. So for example, we made in the previous tutorial a single perceptron. Okay, just Wx plus b. So that cannot be done. It can be done if I make a dense layer of 1 neuron. But if I especially want Wx plus b computation, that cannot be done. Or some other type of learnable functionalities that I want, that cannot be done. Okay. So basically now what I am doing is, now this code has been taken from Google TensorFlow documentation itself with just minor changes of my own, but majority of the code is in TensorFlow documentation. It's been taken from the next 2 codes. Okay, and it's a wonderful documentation. All credit goes to the TensorFlow team. You can just go towards them, see their guide and tutorials. It's a wonderfully written documentation, but please be selective. TensorFlow is such a vast API that you can easily get lost of what you want. Okay, so please be selective at what you check onto it. Be sure that what you are seeing is actually useful for you before going into something, because it's a really complex API and there are a lot of things in it and it's easy to get lost inside the documentation. Yeah. Okay, so about TensorFlow something. In TensorFlow, I have tensors, the variables. Okay, now TensorFlow variables are actually immutable. That is, once I've defined a tensor, its value cannot be changed. But that's not what I wanted. So that's why TensorFlow works very well with Python, because in Python everything is object oriented. I can actually provide an object state, that at what state that my current object is, and using that state, the statefulness of the Python allows me to change the values of a variable and tensors inside TensorFlow. Okay, so that way I can actually have these derivatives, the changeable derivatives, changeable tensors because of Python. So that's why all of these libraries, TensorFlow, CNTK, Keras, and PyTorch are now coming towards Python because of the statefulness property of the Python. And it's really difficult to embed these libraries with other languages like C, C++, and Java. Yeah, they can be implemented with Torch and Lua, because again Torch and Lua are stateful languages. But C, C++, and Java are not stateful languages, so that can't be done. So for that, the first thing is to make a TensorFlow variable. Okay, so if I'm using TensorFlow, one thing is, I will just briefly tell you about the TensorFlow variable. So to make a TensorFlow variable, it's pretty much simple to make a NumPy array. I can just write tf.zeros. Okay, so tf.zeros will make a TensorFlow variable which will contain all zeros, and it will, the size of this variable is 10, 10. Let me just... Okay. Now about TensorFlow variables, since they use the Python statefulness, I can just perform Python's arithmetic operation directly on TensorFlow variables as well. So in this case, what I am doing is I am just performing the Python operation of incrementing each of the values of the variable x by 2. So this will work. So just any normal arithmetic operations of Python will work on TensorFlow variables as well. Plus, minus, divide by, multiply, and so on. Basic arithmetic operations will work. So here you can see that once I made zeros and I have added 2 at each of the element, now the value of tf.tensor is all are 2's. Okay, so arithmetic operations work on TensorFlow variables just as they work on NumPy variables. So this is pretty much, there is something new thing inside TensorFlow 2.0 which was a bit problematic in previous TensorFlow versions, that that thing was not enabled. For any arithmetic operation we had to use TensorFlow's inbuilt libraries, but we couldn't use normal arithmetic operations.
This is in TensorFlow
2, yes sir.
2. This is immutable, I guess you understand. Because it cannot change, so you use Python, this new thing is now being available. So what he was trying to say is that you will have to make the computational graph and then things are going to work, and the tensors, these nodes are immutable. But now you can change using this stuff easily. That is the good thing.
So by the way, basically the thing I'm covering is about Python 2.0, that is the eager execution. This is the latest thing which has just come around few months before. Okay, if anybody later on is working on session APIs, then they can contact me. I can just give you two quick tutorials of the previous TensorFlow versions, online tutorials. I can redirect you towards them. But this is about the newest TensorFlow version of 2.0. Okay. So something about TensorFlow tensor again, or TensorFlow variable is I can convert that variable to a NumPy value with just the function v.numpy. So if I just write the TensorFlow variable v and use v.numpy, it will be converted to a NumPy variable very easily. Okay, so any of the TensorFlow function I can convert to NumPy variable just by using v.numpy. And for a TensorFlow variable, there are yes, you can use arithmetic operations, but there are many inbuilt TensorFlow operations as well. Like there's an assign operation in which you can assign a particular value to a variable. Then there are complex mathematical operations like square, square root, logarithmic, exponential, and so on. So these kinds of operations are already inbuilt inside TensorFlow, and you can use them over the TensorFlow variables yourself. So here they have shown that they have used tf.scare on a TensorFlow variable v, which will scare each and every element of the tensor v. So if I run it, you can see that now after scaring, the assert v.numpy equal to 0 is not giving any error. So that means that the value of v here is 9. Otherwise, if the value of v wouldn't have been 9 in 11th line, the assert would have failed. Okay, so now it's giving me a value of 9. So this is just about, the reason I showed you is that TensorFlow variables are pretty much similar to NumPy variables. But when you are using TensorFlow, when you want to make a computation using TensorFlow, you have to use TensorFlow variables. Okay, you cannot use NumPy variables directly. So that's why, but they're pretty much similar to NumPy variables, although, and there are a lot of functionalities they're already given in TensorFlow documentation. Finally, we want to make a pretty simple model of wx plus b. So it's shown here. We want to make a simple model of wx plus b, where in the final task we want w to be 3 and b to be 2.0. Okay, so this is the task. That's the task we want to achieve. This is the model that we want to achieve, where my weight is 3 and b bias is 2. And using the function of wx plus b. Okay, this is I want to achieve, but I don't know. Okay, this is what I want to achieve. So I will just try to model a simple neuron wx plus b without computing gradients on my own, without coding any gradients. I don't want to code any gradients. Okay, the gradient computation has to be done by TensorFlow itself. So for that, first thing that I will do is I'll have to make a class model. Okay. So my first task is to make a class model. Now this model will provide, now how I define a model? Here a model is defined by the one neuron. Okay, that neuron has a weight and a bias. So that's my model. Just model is defined by the trainable parameters and some non-trainable parameters as well. That model has, that the computation has. So if I say about a deep learning model, then all of the conv layers and all of the dense layers, so each of them have some trainable parameters, right? So a combination of all those trainable parameters is called a model. And here my model is defined by just two parameters, my weight and bias. That's defining the model. Okay, so I will create a class of model. Here I am defining the model. Now first thing while creating this class is I have to initialize this class. Okay. Now in this initialization, what my task is to initialize each of the variable each of the parameter that I want to optimize. So in this case, I want to optimize two parameters, weight and bias. So while creating this model, my first task is to initialize my weight and biases. Okay. So for that, what I am doing is I am calling So I'm having two variables inside this class, W and B. Okay, and I'm calling them by self.w. What self.w does is, for a particular object, it will take the value of that object itself. Self means I'm calling my own object's W value. Okay, let's say I have an object here. I've called an object model of this class model. So for model object, by calling self.w, I'm saying that for my own object, I want to call the W value. Okay, so that's why we write self.w when we are calling the any variable of the same object. Because in Python, there's something really good is that you can actually communicate between the variables of multiple objects inside a class. You can actually do that. So if you don't want to do that, you just want to communicate with a variable of your own object, you need to make that object as self.w or variable as self.w. Okay, so whenever you are coding in Python in a class, always use self.w and self.v, so that to make sure that you are working with that object's variable only. Okay. So basically, I'm first initializing self.w is tf.variable 5. I'm just initializing the weight as 5, and similarly, I'm initializing the bias as 0. Okay. Now I have to make a forward pass. Okay. So to make a forward pass, there's a property in Python object-oriented programming. The property is now here for any class, if I've got the object of that class. Okay. If I call that object as a function, right? If I call that object, inside the class, a particular function will automatically be called. That function is defined by underscore underscore call underscore underscore. Okay. So this is a function at the 8th line, the call function. So let's say I created an object of a class. Okay. Now if I use this object as a function anywhere, by default this call function of the class will be called automatically. So this is a property of a Python class. Okay, it will automatically call the call function, right? So by call function, what I mean is that when I am calling a model, what I want? When I call a model, I want a forward pass. I want a computation of wx plus b. That's my model, right? I will give an input to the model, that is my x, and the model needs to return me wx plus b. So that's my model. So that's what I will define in the call. So the call function will take the object on which it has to be called, that is the self, and the input over which it has to be called. So the call function will have two arguments, the object as well as the input. So over this input x, it will perform wx plus b and it will return it. So whatever you define inside the call, inside this underscore underscore call function, that will automatically be run once you just run the model, the object of it. Okay. Is this part clear to everyone? Because this is a fixed notation for, you can actually go into more details of it about Python, how Python objects work. You can actually go into more details, but this is one of the property of Python objects. So finally what I do is I here call this class and get an object of this class model. Okay. Now inside this object of the class, once I have called this object, the initialization would be run on its own. Right? The initialization have initialized my weight and biases at 5 and 0. So if I pass 3 as an input towards this model, what will be the output? 3 into 5, 15 plus 0, 0. Right? So there I what I have done. So towards this object, I have passed 3. Okay. So what it will do is, it will automatically go to the call function, use this x, compute wx plus b and return me 15. So if I want to make the forward pass, I just need to pass a value in the model, it will return me the value of the forward pass. So this call function is automatically called whenever I call this object. Okay. So now this way I have an object model in which my weights are defined as well as my forward pass is defined. The forward pass in which I need to optimize. Finally, I want to define my loss function, because the loss function would be on which, now I have defined a forward pass, right? This is the forward pass. Now my task is to define the loss function. Here the loss function is just an MSE loss function. I have said by using, it's a mean square error. That is, I am taking the predicted y, target y, scaring them, and then mean, scare, error. Simple. It's just an MSE loss. Okay, I've written using TensorFlow operations. Right, MSE loss I've written using TensorFlow operations. Okay. Excuse me. Now my task is to create the data for training this system. Now the system is complete. There's a forward pass I have defined with variables and the loss. So here I'm just creating some random data for this system. I'm not going to the detail of the code, it's just a normal code. And you can see that the blue lines are the data of the system. For where I want the W to be 3 and B to be 2. Okay, the blue lines are the data of the system. And red lines are the data of the initialized system. I have initialized my model to something, right? There's a red line. You can see there's a high error. The red line is not aligned with the blue points. So that's my task. I need to make this red line now using gradient design to be aligned with these blue points. Okay, so blue points are my data on which I want to train, and red line is my initialized line that I have, initialized regression line that I have got, and I want to align this. Okay. Now for doing that, first of all, I need to define a training loop. Right. Now inside the training loop, what is important is that I need to define the gradients. Okay. So what happens in the training loop is, so this is a function train. Please listen to this very carefully. This is the main part of TensorFlow 2.0. Okay. Now define a function train. This function will take a model as input, that is a model object, that the model that needs to be trained. Then on the input it has to be trained, the output that I want the model to deliver, and finally the learning rate, at what learning rate the model needs to be trained. Okay. Now the second line, with tf.gradient tape as t. Okay. So what does this is? It creates a block of code. The property of the block of code is whatever I write within this block of code inside the gradient tape, it will keep on recording its gradient as I keep on writing the computation. So inside this, inside the gradient tape, so here in the second line, I'm initializing a gradient tape. What is meant by gradient tape? That I'm creating a tape. You know what a tape means, right? Tape is something where I record something. I'm creating a record of all the gradients that I need to compute. Okay, and those gradients will be computed by defining the forward pass. So inside the gradient tape, if I keep on defining the forward pass, for that complete forward pass, it will keep on taping, it will keep on recording all of the gradients on its own. So here I am saying with tf.gradient tape, that is with the property of recording the tape as t. That is, it will keep on recording all of the gradients inside t. Okay. Then I will write the computation over which it has to record the gradients. Since it has to record the gradients in a simple forward pass here in itself. So now what was the forward pass? I have an input, I pass it through the model, and then I compute the loss. Right, this is my forward pass. Right. So I have now inside the gradient tape, I have given my forward pass completely. So once I have given my forward pass inside the gradient tape, it will automatically record all of the gradients that for each of the variables inside this forward part in t. It automatically does that. You don't have to do. You just, for any forward pass for which you want to record the gradients, you just write them as with tf.gradient tape as t. Okay, it will automatically record all the gradients. And finally, when you want to choose some particular gradient, okay, you want to choose some particular gradient, what you do is you call t.gradient. Okay. First argument is the value of which the gradient, or the value that you have to minimize. Okay. First argument in the t.gradient is the value that you have to minimize. And the second argument is the list of trainable variables through which you have to minimize. Okay, so what this t.gradient will now do is, it will compute gradient of current loss with respect to the weights and give me the dw. And similarly, it will compute the gradient of current loss with respect to the bias and give me dB. Right. So this way now, using the gradient tape as t and then recording all the gradients, and then from that t dot gradient, computing the gradient of loss with respect to my model weight and model bias. Now since I've got the gradient, I can just update my model weight and model bias using assign subtraction. See, assign subtraction is an inbuilt function. What does it do? It's equal to a minus equal to 1. Assign subtraction. That what it will do is, it will take the value w, okay, subtract the value in the brackets from the w and assign it. W is equal to w minus learning rate into dw. Okay, so for the computation, we have a function called assign subtraction that will first subtract a particular value from a variable and then assign the new value. Okay, so finally what I will do is, since I have got the dw was my gradient, I multiply my learning rate towards this gradient, and now I want to subtract this entity from my weights, right? So for that I am using the function of assign sub, and similarly I am doing that for my bias. So now in this function, train function, what I have done is, given any sort of inputs, I have computed the loss, computed the gradients, and then I have updated my model weights and biases inside this train function. And by using gradient tape as t, I didn't have to define any gradients. The gradients were automatically computed by TensorFlow.
So my question is that given this gradient tape, I have so for all of my data, first I compute the loss with respect to this whatever the model and the outputs, and in that gradient tape t, everything got recorded. So that is my first 2 and 3 lines. First they execute over the whole data.
No sir, they will actually, this is eager execution now. It's not making a computational graph right now.
Okay.
So it will take a batch of data.
Yes.
Over that batch of data, it will execute 2 and 3.
Okay.
2 and 3. And over that batch, now based on 2 and 3, it will compute my gradients and then update it.
Yeah, so which means that 2 and 3 over whole data, first it's being done.
Over the batch, yeah.
Over a batch, and you know, we have got everything being written in this t, and then t dot gradient is doing this back propagation.
T dot gradient is just giving me the gradients. Yeah, it's doing the back propagation, the chain rule. It's applying the chain rule now.
T dot
Gradient is applying the chain rule.
And we have got this, and they will have to tell that what we will, what is the thing with respect to which we wanted to differentiate. So that is essentially del current loss of del W and del T.
Yeah.
In one pass we can do that. And that is, I guess, that via computational graph internally, so they have come up with
this.
And the 5 and 6 is at least model update.
Yeah, these are just update equations.
So 4, 5 and 6. So my question now is that given this full T, if it is the case, then full T has got all this data first.
Yeah.
For a batch. Then T dot gradient is going to give me 1 by 1 dw by dv, or it also give me a set of
no, a set of gradients for each of the input.
And then set of updates are going to happen, all of them in one for 5 and 6.
Yes, sir. No, actually sir, in this case it won't give set, because see, you can see while defining the loss function, I have already defined the averaging. It's a mean square error loss function. So it will already, when I'm inside this, gradient tape will take all the inputs. But now the loss function is already averaging out. So it's just a one value for all the inputs that I'm giving.
So, okay, so that is one batch, one round of update.
Yeah,
one batch, one round of update.
Yes sir. Overall total added loss.
Oh, so that 2 and 3, that shows a type of loop which is actually saying that see all the data and average out and get the loss. I'm taking writing everything.
Yeah.
And then do the T gradient once directly. dw and db we have got, and 5 and 6 is the single update. Because one batch, one update.
One batch, one update. Yes sir. So this is important, because in this way you can realize it was a simple model. One might ask a question that why for such a simple model where I could just write the gradients in just one line of code, I'm doing so much. But here what I want to show is this thing can be scaled to any amount of complexity. This thing can be scaled to any amount of complexity, to any amount of outputs you want to optimize. onto any amount of variables you want to optimize. You can create multiple gradients as well. You can optimize multiple values. You can have multiple training variables. Even you can have partial gradients. Let's say you want to optimize a loss with W but not with B, but you want to optimize some other loss with B but not with W. So even that can be done. So partial derivatives. So all of these things can be easily done for complex trainable models, can be easily done using gradient tape. So gradient,
when you have multiple types of loss and complex function that you want to do somehow code, not one single thing. So anyway, it is very easy using tensor our Keras model. But suppose that you wanted to have multiple losses. So he has shown you a very simple thing in which stochastic gradient descent is happening. Now, if you wanted to change the optimizer, probably will have to write more over here. I mean, SGD and other things directly.
I will show in the next one how I'm using SGD also.
Okay.
Adam also.
Adam and all. Okay.
In the next one. So, see the point when we use these APIs, these TensorFlow APIs is that if you take any latest paper, right, many latest paper will have some layers or will have some loss functions or will have some computation that is not defined in Keras. So once that computation, once that layer or once that loss function is not defined in Keras, you cannot use Keras. So for that you have to come up to such function, because if you are given any computation and you are able to code that computation in TensorFlow, TensorFlow will record the gradients of that computation for you. You don't need a problem to make a layer out of it. Okay, and this is a solution for your first assignment, second question as well. You can see the solution here. Without using the layer API of Keras, you can use such a system of gradient tape to optimize, to write your second question of your assignment 1. Okay. So finally, here is my training loop. So inside this training, I will just run this. Okay. So this is my training loop. Okay. So inside this training loop, first of all, I am creating an object of that model. Okay. I am creating an object of the model. Yeah. See, gradient tape, another thing about gradient tape is, it will also, my values that I am updating, whatever are my trainable values that I am updating, the losses and everything, gradient tape will keep a history of everything in itself. Okay, my metrics, my losses. I will show another example later on of how gradient tape keeps the history of your losses as well as accuracies as well. But here gradient tape will keep an history of my W's and B's by weights and biases on its own. Okay. So now let me say I'm running this code for 10 epochs. So what I'm doing is initially, once I have called this object model, my weights and biases, they have been initialized, right? Now they have been initialized. So what I'm doing, I'm just appending my initial weights and biases values. For keepsaking, I want just to know how my weights and biases changed. Okay. Then I'm passing these inputs. I'm passing those inputs to the model and getting the loss. Okay. Now that means saying for the current model, my loss will be the current loss for my current given model once I'm inside this training loop. Okay. No training is happening right now. For just a given model, I'm just computing my current loss. That I'm passing the input to the model and then computing the loss with respect to the output. I'm just computing my current loss. Finally, what was the name of this function? Train. To this train function, first thing is first thing is I pass the model. So to this train function, I'm passing the model. Second thing, I'm passing the inputs. Here I'm using all the data completely. Here I'm not using any batching. I'm just providing all the data completely. And finally, giving the corresponding outputs, providing the learning rate as 0.1. Okay. And once I call this, it will automatically train the whole model, because on the train function I've already defined update equation as well. You can see the 50 and 60 equations are updated. So once I call this train function, now my weights and biases have been updated. Okay, now my weights and biases have been updated. So finally I print for that epoch what my weight and biases and loss were, and since my weights and biases are updated, for the next time if I when this loop will run, it will run via the updated weights and biases. And over that updated weights and biases, it will again run the train function over the whole data and then again update and so on. So it will keep on iteratively updating the weights and biases till the time a loss converges. So if I just run it once. So you can see on epoch 0 my loss was 8, whereas till epoch 9 my loss come to 1. And here in the curve you can see that the dotted lines was the weight and biases that we wanted to achieve, and the curved lines were the normal straight lines. They are how the weights and biases kept on changing, and till a point they came up pretty close to the desired one. And if we run it for many epochs, they come pretty close to what we actually desire. So this is how you use TensorFlow's gradient computation to make any learnable model, any type of learnable model that you want.